Hi, in this video, I want to show how we can use the geometric series to derive the power series for many other functions by combining the geometric series with algebraic manipulation. So if you're good with algebra, you can apply your algebra to a lot of functions to make it look like the geometric series and then go from there. There are also techniques of using calculus, using derivatives and integrals to apply the geometric series to other functions, and it's not part of this video. This video shows you how the geometric series is already useful just with algebra. What is the geometric series? The geometric series is a series you see on the screen right now. It has powers of x on one side for n from 0 to infinity, and the answer is 1 over 1 minus x. The geometric series only works if the absolute value of x is less than 1. That would be the interval of convergence of the geometric series, and in fact, in that interval, the geometric series is absolutely convergent. That will become important in a bit. So the key to this, the trick to this is if you have some other function, but if you can write it in the form 1 minus some quantity y, then you can apply this geometric series and write it as sum of that quantity y to the power n for n from 0 to infinity. And you also know what the interval of convergence is. The interval of convergence is that the absolute value of that quantity y is less than 1. As soon as you can write your function in this form, everything else follows. So let me show you some examples. Let's take 1 over x squared plus 1. How can we write 1 over x squared plus 1 in the form of 1 divided by 1 minus some quantity y? Okay, I got the right numerator. I got a 1. And this is a minus, and I don't have a minus, so I have to just create one. 1 over x squared plus 1. First of all, I'm going to put the 1 in front. And then because I need a minus, I'm going to write the plus as minus minus. And now I have it. I have it in the form 1 over 1 minus some quantity y. So I know that it is equal to the sum of that quantity y to the nth for n from 0 to infinity. And I expand out the algebra here. The negative to the nth, I'm going to write it as negative 1 to the nth. And then I have x squared to the nth. That's x to the 2nth. And that's my answer. And I also know that the interval of convergence, of absolute convergence, is that the absolute value of that big quantity y is less than 1. So that means here the big quantity is minus x squared. Then I'll just solve this inequality. Because of the absolute value, the minus doesn't matter. And x squared, absolute value of x squared is less than 1, is this equivalent to absolute value of x less than 1. So here's my answer, the power series. And here's my answer for the interval of convergence. I've just written the power series for 1 over x squared plus 1 without having to take the first derivative, second derivative, or any of that stuff. Let's do another example. X over x squared minus 3. So this one is a little bit harder than the previous one because I don't have 1 in the numerator and I don't have the form of 1 minus something or 1 plus something in the denominator. Instead, I have something minus 3. Okay, so I'm going to fix it one at a time. I want it to be in this form. 1 over 1 minus some quantity y. I have x in the numerator instead of 1. If I want 1, I factor out the x. That takes care of that. I want a 1 minus something, or at least a constant minus something in the denominator. I don't want something minus a constant. I want the constant minus something. I have it in the wrong order here. So if I want to switch the order, I just factor out the minus 1. If I factor out a minus 1, then I have the subtraction in the order I want. So I factor out a minus 1, I put that in front as minus x. Okay, so I got this down. I need that. That's the last thing I need. I have a 3, I need it to make it into a 1. So what do? I factor that 3 out. When I factor the 3 out, then the 3 becomes a 1. The x squared becomes x squared over 3. Now I have the form I need. I have the form I need. I'll just write the power series, the geometric series. And I may want to do some extra algebra on the inside of this series. X to 2nth be divided by 3 to the nth. Some people may want to multiply the x third back inside and change the powers here. But I think I will just leave it like this. And now what is the interval of convergence? The interval of convergence is that this x squared over 3 has to be less than 1, which means the same as absolute value of x squared has to be less than 3. And I take square root both sides. I have absolute value of x is less than radical 3. There we go. That's my power series, and that is my interval of convergence. All right, let's do something harder. This rational function, how do I convert this into a power series using the geometric series? It doesn't look obvious at all. I'll do what I can. I can try factoring this up. 1 and 1, plus and plus. Plus 2x plus x is 3x. Yeah. Oh, now I know. Now I know. If the denominator can be factored like that, then the whole fraction, the whole rational expression can be broken into 2 fractions with the 2 separate denominators. That's called partial fraction, right? And if I can have them in this form, then each of them can be written in the form of 1 minus something in the denominator. And then that means I can apply, or I can use the geometric series. So yeah, I'm gonna do partial fractions. This is equal to something over 2x plus 1 plus something else over x plus 1. And because that is just x, then this is just some constant a, and that is just some constant b. Common denominator. And that means I can equate the numerators there. First, I'm going to let x equals -1. Then on the left-hand side, I have -3 plus 2. 3x plus 2 becomes -3 plus 2. And on the right, the a term is 0, and the b term is -2 plus 1. -1 equals -b. b equals 1. I got one of my constants. And I plug back in with x equals 0, b equals 1. Then I have on the left, I have 2 is equal to a plus 1 times 1. Then a is also equals to 1. So the given function is equal to a over 2x plus 1 plus b over x plus 1, and both the a and b are equal to 1, so it's like this. And now each of them can be written as a geometric series. The first one is 1 minus negative 2x like that. And the second one is 1 over 1 minus negative x. And when I have a negative like that, it indicates an alternating series, so I should factor out the negative 1. Great, so now I have 2 power series. Awesome. Can I make this into 1 power series? Yes, I can make this into 1 power series given certain condition. What are those conditions? Those conditions have to do with the interval of convergence. So I have to check the interval convergence of these 2 series. The interval convergence of the geometric series is that the absolute value of this thing here has to be less than 1. Same over here. So for the first series, this has to be less than 1. And for the second series, this has to be less than 1. Second series translate into absolute value of x is less than 1. And the first series, it translates into, first of all, because of the absolute value, the minus sign doesn't matter. And then I divide by 2, I get absolute value of x is less than 1/2. Let's take a look at the number line. On the number line, let's say if this is 0, then the first series says it's convergent between negative 1/2 and 1/2. The second series says it's convergent, actually absolutely convergent, between negative 1 and 1. So within this interval here, both series converge absolutely. And when you have 2 power series that converge absolutely on a shared interval, we can apply a theorem that says we can just combine them together term by term. This is the theorem. The theorem says if you have 2 power series and they both converge absolutely for some interval, absolute value of x less than or, then we can combine them term by term. Not only combine term by term, here's one series and here's the other series. We can combine them term by term, but each term, if we need to, we can multiply by some extra constant on the outside, alpha and beta, and combine them too. So alpha A, beta B, let me make the algebra a little clear. If I multiply this in, and then I add them term by term, then I have alpha A sub n x to the power nth. That's after I multiply in the alpha in the first series. In the second series, after I multiply in the beta, I get beta b sub n x to the nth. And what this theorem says is, even though they are sitting in 2 separate series, I can combine them into 1 series by erasing like that and actually adding them and combine them into 1 series like that. And once I've combined them, that means I can factor out the x to the nth, and I end up with sum of alpha an plus beta bn x to the nth, and I have this. And in this combined series, first of all, not only is it equal to what I started with, but it also converges absolutely for the same interval. The same interval absolute value of x less than or. This new series also converges absolutely in that interval. So that's why the interval convergence is important when we manipulate these power series. We need them both to be absolutely convergent in order to do this kind of term-by-term combination. So going back to our 2 series, they do share this interval of convergence where they are both absolutely convergent. If they don't share any interval convergence at all, then we cannot do this, but they do. So now we can combine them term by term. We can basically write this term plus that term and put them under one single sigma. They start out with separate sigmas. We can combine them into one sigma thanks to that theorem. Like that. And it was -1 to the nth, 2 to the nth. So within this interval of convergence, I can combine them like that. And I can do two things. First of all, they have a common factor of -1 to the nth, so I can factor that out. And they have a common factor of x to the nth, so I can factor that out. And what I have left is 2 to the nth plus 1. And that is my answer. And the interval convergence is going to be that one. All right, so the general approach is to use algebra to arrive at the form 1 divided by 1 minus some quantity y. The algebra involved maybe factoring out something. It could involve factoring out a factor of -1 in order to switch order of things, involve writing any addition as minus a negative. It may involve partial fractions, and obviously it may involve all of the above. And at the end of the day, the interval convergence is that the absolute value of that quantity y is less than 1, which you will then need to solve for absolute value of x. All right, hope that helps. Any questions or comments, put it in the comments section below. Like, share, and subscribe for more contents, and thanks for watching. Bye.